So next up, would like to introduce Nancy Shaw, who will be presenting on network ASICs. Nancy's a distinguished engineer at Juniper Networks and traveled here this week from Sunnyvale, California. This is Nancy's first time presenting today. So please welcome to the stage, Nancy. Thank you.
Hi, everyone. Thanks for joining. So a key component in any network router is the network ASIC. Whether you want to increase the bandwidth of your router or implement complex routing protocols, forwarding protocols, it's possible because of the network ASIC and the advances we've made in network ASIC design. So in this tutorial, I am going to first go over the basic components of a network ASIC. So what is actually in the ASIC. Then I will go over in more detail some of the architectures we use in implementing key components, the packet processing and the buffering systems. And finally, I will highlight some of the challenges we face in developing our next generation of ASICs. So starting with some terminology. ASIC stands for Application Specific Integrated Circuit. You may be more familiar with the term chip. ASIC is just a chip. But as the name implies, it's a chip that's specially designed for a particular purpose. So the network ASIC in particular is a custom designed ASIC that implements networking protocols, networking functions, anything that makes the network operate. And so there really isn't a strict definition of ASIC. You can call any chip an ASIC. So the router has actually quite a few ASICs on it. So if you took a typical chassis-based router and you took a look inside, you'll probably see line cards, fabric cards. There's an ASIC on that fabric card as well. And the purpose of that ASIC is to provide all-to-all connectivity between line cards. And then if you look at the line card, there's another ASIC. And that will be the focus of my presentation today, the ASIC on the line card. And that ASIC connects to the network through optical cables and optical modules on one side. And then it communicates with fabric on the other. Okay, so let's take a look at step-by-step what's actually in this ASIC. So the first component you'll see in the ASIC is the serializer, deserializer, or SerDes for short. And the purpose of the SerDes is to translate serial signal into a parallel signal. And in the reverse direction, you'll see it convert parallel to serial. And so we use a serial interface at the input and output of the ASIC because there's advantages to using a serial interface. With serial interface, you get fewer traces on the board, you can have less noise interference, and overall better signal integrity. And because of that, you get a higher frequency signal. You can send data at a higher bandwidth. And so overall, you actually can send at a faster rate than if you had a parallel bus. So actually, I forgot to mention that if you look at this diagram here, you'll probably see that it's clearly divided into two parts. There's an ingress part and an egress part. So when inside the ASIC, we refer to ingress as packets coming from the network, passing through the ASIC and going to the fabric. And then on the egress side, we go from fabric to the network port. So you shouldn't confuse this with the ingress router and egress router. So when I'm referring to ingress and egress, it's within the chip itself. Okay, so continuing on, the next block you would see is the network interface logic. And this is what translates the bits and bytes that we see from the SerDes into packets. And so this is where you see the framers, the descrambler, anything related to translating and understanding the bits. And it's usually done according to Ethernet standards, so the IEEE Ethernet standards. And then you'll see a data path. So we want to process packets in the ASIC, but it may not be the most efficient way of transferring data in the ASIC. So depending on your architecture, you may want to divide the packet into smaller pieces. You may want to pack multiple packets into its larger structure, whatever is more efficient for transfer. And then comes the packet processing block. So this is where we actually look at the header. So generally, we look at the headers and we do things like parsing, classification, route lookup, firewall filters, any kind of manipulation that we need to do to make sure that when the packet gets sent over the chip, the next router would understand the packet. And then after that, we always have a buffer. And the purpose of the buffer is to hold packets during periods of transient congestion. So the whole purpose of holding that packet is so we don't drop. So we all know that there are performance degradation, when you start dropping packets. So we need to size this buffer so that we can absorb these type of transient congestion situations. And then the way we actually store the packets, manage the packets in the buffer is in queues. So just like how you have to stand in line at the grocery store waiting for your turn, well, we have queues, lines of packets waiting to go get transferred out of the ASIC. And each of these queues represents a different priority or a different QoS or class of service. And in this way, we can apply different scheduling policies per queue. And then finally, we have the fabric interface. So this is where we implement protocols to translate packets, to send packets across the fabric. And this is basically the same thing what we did with the networking interface. And here we also have SerDes. So basically, we use SerDes for any kind of high bandwidth transfers of data into and out of the chip. Okay. So, what really differentiates, so this is a very high level view of what's in the ASIC. But what really differentiates one network ASIC from another is the implementation details. And there are many different ways of implementing these components. So let's take a look at in more detail some of the implementation options we have, starting with the packet processing. So in terms of packet processing, this is where we actually look at the header and process the header. I'm going to talk about two different architectures. So on the one side, we have this multiple packet processing engines, or PPE for short, architecture. And on the other side, we have a pipeline architecture. So let's go into more detail. So with the multiple PPE architecture, what you will see is this large array of PPEs. Each PPE operates independently of each other, and all the PPEs operate in parallel. And each of these PPEs has the capability of executing the same type of functions. And the way these PPEs work is that they access memory, instructions from memory that actually tell the engine how to treat the packet. And this memory, instructions are completely software programmable. So you have very high flexibility of what you can do with the packet. So this type of architecture, you can implement any type of protocol that exists today, and probably any protocol that exists in the future. So very highly flexible. So what happens in this type of architecture is the packet gets dispatched to one of these packet processing engines, and it stays in that engine until complete. And so we sometimes call this run to completion architecture. Now, there are disadvantages to this architecture. You get that high flexibility, but there are consequences. There are downsides to this flexibility. There are costs to the flexibility. And one is latency. Latency tends to be very unpredictable because it really depends on the software. It depends on how many instructions it takes to finish a particular packet. So more complex packets may take longer, less complex may take shorter time. It's all very kind of unpredictable. And then you also pay the price of higher, not as high performance output, and also what we call more area. It takes more logic to actually complete this type of architecture, especially when you compare it to our next architecture, the pipeline architecture. And in this architecture, what we have is a series of blocks, and each block does a very particular function. So you would have one block that does classification, does parsing, one that does classification, one does firewall filter. And because we know what this block does, we can actually optimize that block, and in some cases even hard code that block to do a specific function. And so we can highly optimize this architecture for performance, for lower power, for lower latency. And basically, a packet that enters this pipeline, this architecture, has to pass through every single block. So there's no shortcuts through this block. So then that means that latency is very well understood. It's very predictable. And if the packet needs to be processed more than it can be done in one pass, then we have options to actually recycle the packet or recirculate the packet into this pipeline a second time. But again, it's a fixed latency, in which case you can predict what kind of latency it would be at the end. And so, like I said, this kind of you can get high performance because of the hard-coded logic, of the dedicated logic. You can decrease, because you have dedicated logic, you have lower power, lower area, lower amount of logic that you need to implement. So let's take a look, just to summarize what we have in these two different architectures. With the multiple PP, you get ultra flexibility, just infinite programmability, but you might not be able to support the higher speeds and higher power, lower power as the other architecture, the pipeline architecture, where you can have the highest performance, the lowest power, the lower latency. And in most cases, it pretty much covers most of the cases that you want to support. But then you just don't have that flexibility for maybe some future protocols. So I think I've described two extremes in terms of flexibility, two types of architectures on the two extremes of the spectrum. But obviously, you can always design something in between. Okay. So let's take a look at the buffering architecture. So what we said earlier was that we need this buffer to provide storage during periods of transit congestion. And each queue is representative of a priority or a class of service, quality of service. So here we have two buffering architectures. On the one side, we have what we call the two-stage buffering, where we buffer both on ingress and on egress. And then we have the second option is the ingress-only single-stage buffering. So let's take a look more closely at the single-stage option. So in this option, we have a buffer on ingress. And we have a small buffer on egress, but it's nowhere near large enough to do any kind of QoS. So it's really just there to have packets on deck on the egress to be sent out. Okay, so for ingress-only buffering, we implement this concept of VOQ. VOQ stands for virtual output queue. And virtual output queue is just a virtual representation of an egress queue based from the perspective of an ingress side of the chip. And so we implement these queues basically on ingress rather than on egress. There is no actual queuing happening on egress. Once the packet arrives on egress, it can actually go out of the chip. As you saw, a very small buffer. It's really just buffering temporarily just to go out the chip. And so if you see in this picture, for every single egress port, in this example, we have one egress port, and say this egress port has 8 queues. In that case, we need to implement 8 VOQs on the ingress. And so for every single egress port, as we add more egress ports, we add more VOQs on that ingress. So here we have 4 egress ports, then we have 4 times 8 VOQs on ingress. And the advantage of having this type of architecture is that there is no head-of-line blocking. So when we say head-of-line blocking, it's when we have a packet at the start of the queue that maybe is flow controlled. It cannot make forward progress, in which case it blocks all the packets behind it. And this can happen if you have a queue that maybe you put both low and high priority packets in the queue. And say the low priority packet is at the head of the queue, and that low packet priority, the low packet has been flow controlled, so it can no longer be popped out of that queue. And so any high priority packets behind it are now stuck. And now you violated your priority scheduling. But in the VOQ case, we actually have a queue on the input that represents every single egress queue on the output. But the downfall for this kind of architecture is scale. And the problem here is that that VOQ that represented that egress port has to be replicated on every single ingress chip. So if we had 4 different ports here, we basically have to replicate that 32 VOQ on every single ingress chip. So you're kind of, because of this replication that's happening, you're not getting the scale that you could have if you didn't have VOQ, because you technically have 32 times 4 queues that you're supporting, but you really only have a scale of 32. And the reason why we have to have this VOQ replicated on every ingress is because we can't predict where this packet is coming from. It could come from any ingress port to this particular egress port. So now we have to have that VOQ represented on every single ingress chip. Okay, so the next architecture is the two-stage buffering architecture. And in this architecture, like I said, we have buffering on both the ingress and the egress. So what happens here is that we buffer on ingress, and we have a queuing structure on ingress, but it's not a full full number of queues. It's a smaller number of queues just to prioritize packets that need to get sent over the fabric. Whereas here in this architecture on egress, once the packet arrives on egress is where we see a large number of queues. And because these queues are local, so they only can be used by the local egress, and they're not shared by all the other egress ports in the system, we can have higher scale. So the more line cards, the more chips, the more egress queues, they add, right? Here we have 4 times the number of egress queues. So our scale is actually the total 4 times the number of egress queues. Okay. So to summarize, we have our 2-stage buffering, which we said we can achieve a very high scale because these egress queues are not shared. They're only used by that local port. And so because we have a large number of queues, we can support complex subscriber and QoS management. But then because of that small number of queues at the ingress, you may have header-line blocking because there's no one-to-one mapping between egress queue and ingress queue. And then on the ingress-only single-stage buffering system, we have no header-line blocking. But then you may not have the ability to achieve the high scale of the 2-stage buffering. Okay. So, how do we choose the architecture that really suits the needs of? So we have to take a look at some of the design requirements. So some things like scale. We talked about scale of number of queues, but we also need to consider scale of the route scale. There's not a lot of other factors that we need to consider scale. We also have to consider what kind of performance we want for this chip, what kind of port speeds we want, what kind of total performance we want from the ASIC. And then we also want to consider what kind of features we want to support, whether we want flexible feature support or hard-coded is good enough. But there's this whole other aspect of ASIC design, and it has to do with the development and manufacturing of the ASIC. And this is where we have to consider things like area, so meaning the size of the ASIC, because there are limitations that the manufacturer provides us that says, you can't make a chip bigger than this size. We also have to consider power. So the more logic in your ASIC, the larger the ASIC, the more power your chip is going to expend, and the more power means more heat. And if you can't dissipate that heat, then your chip overheats and it doesn't operate as well. It doesn't operate properly. Or you also have to consider how fast you can run the clock in your chip, and that will affect what kind of bandwidth speeds that you can support. And finally, obviously, cost is the biggest factor. If you can't make your chip cheap enough, then it's really not worth making. So let's take a little more detailed look into the development challenges that we have in ASIC design. Okay. So it's just a few more terminology. So when we say a die, it's really a piece of silicon, raw silicon, which contains all the integrated circuit, the design that you've placed in that you want in that die. So it's just a piece of silicon, spare silicon. And when we talk about package, it's the container that goes around the die. And the package is important to protect the die against things like moisture, against particles in the air. It also provides connectivity from the die to the board. And so when we refer to chip or an ASIC, it's usually going to be a packaged die. And then I think we all know the biggest factor in ASIC design and any kind of chip design is the process node. So process node refers to the manufacturing technology used to build that ASIC. And you've probably heard of terminology like 3 nanometer, 2 nanometer, which refers to kind of the dimension that's being used to manufacture that chip. And there are many generations of process nodes, and with each generation, that number decreases. meaning the transistor size is becoming smaller. But there are other benefits from going to a newer node. Not only do we have smaller transistors, we also have lower power per transistor, and we also have faster transistor. So the transistor can be run faster. So if you look at the trend of what we've seen in the past of how ASICs have been developed, at the beginning of the 2000s, early on, what we saw is a rapid increase in transistor densities and transistor speeds, and it followed Moore's law pretty closely. So I'm sure you're all familiar with Moore's law. It's just an observation by Gordon Moore that the density of transistors increases by doubles every 2 years. So we saw that pretty closely at the beginning of 2000s. And because we were able to run our chips at a half faster speed, we were able to build ASICs, higher capacity ASICs, without having actually changing our architecture very much. All we really need to do is design in the newer node, run it faster, and then we were able to achieve higher capacity. And because we were able to integrate more, meaning do more with the same area, we were able to build fewer and fewer ASICs to do the same type of work. And in the next decade, what we saw was things were changing. What we saw was that the transistor speeds were flatlining, so we were no longer able to achieve the higher rate of increase in clock. And then we were also seeing the densities increasing, which is good. So we had to take advantage of the fact that we were increasing density, and then design for the fact that we could not increase our clock speed as much. But this is also the period where we were facing the memory wall. I think memory wall was a terminology that's been around for a long time. It refers to the widening gap between the processing speed of an ASIC and the access speed of a memory. And generally for networking, we use external memory for buffering purposes because this way we can actually have very large buffers for this purpose of storing packets during congestion. So because of these limitations like the memory wall and because of the limitations of the speed, we were actually forced to change our architectures. So instead of just increasing our clock speed, we had to do things like more replication of data paths, of packet processing to achieve the higher bandwidth ASICs. And this is about the time also that we started to use this new technology called 2.5D integration. And all that really means is that instead of having a single die within the package, we now can put multiple dies in the package. And this was used for integrating high bandwidth memory, also known as HBM, into our package. And because it's inside the package, you can actually create interfaces between your chip in the memory so that it can run much faster than if you had two ASICs side by side on the board and having to communicate over the board. So now in the future, as we said, we had to change our architectures to address the fact that we couldn't increase our clock speed as much. But because of that, our chips are starting to grow bigger and bigger. And at some point, we're going to hit this limit that the manufacturers have given us, that they cannot build a die bigger than this size. Which means that, again, we need to innovate and create new architectures. So what we are doing now is we're taking advantage of this 2.5D integration by dividing our design into pieces so that we can build smaller dies and connect them using protocols that we can develop, or the vendor can provide, and have higher speed internet between these dies within a same package. So in summary, what we're seeing because of the dependence on process, in building our ASICs, what we see for future challenges is the process node limitations. So we're already at 3 nanometer. We already know 2 nanometers coming up. 1 nanometer is in the talks. But the question is, what is going to happen after that? Can we go any lower? Do we need to change our material that we use away from silicon to some other new material? And if we do change that material, what kind of characteristics of this process node will we get? And so do we need to build new architectures to address those new characteristics of the process node? And then also, we need to handle this problem of increasing ASIC power. So even though every node we decrease power per transistor, we're packing more and more transistor into the same area. And overall, we're actually increasing power. And as you increase power, you increase the amount of heat generated. You need more and more advanced cooling methods to keep that temperature down. Otherwise, your junction temperature within the ASIC gets so high that the ASIC just doesn't function anymore. We are already using very high, sophisticated power-saving techniques within the ASIC in our designs, for one, in the way we design our architecture, but also in the way we try to decrease power by using techniques such as clock gating, where we stop the clock for certain parts of the ASIC that are not being used, and we stop the clock for certain portions of logic that dynamically may not be used at that particular cycle. So as you see, we've had to change our ASIC design implementations over the years to address issues or changing characteristics of process nodes. And I'm confident that in the future, we can overcome these challenges as well with new innovative ideas. So that's all I have. Thank you for listening.
That was excellent. I really got a lot out of that. Any questions? Chris.
Chris Woodfield, unaffiliated. You mentioned stopping the clock or possibly scaling down the clock for inactive logic portions. Is that triggered by, say, a switch configuration, or is it triggered by maybe an earlier stage examination of the packet that's going through the pipeline?
Yeah, so usually you have more effect of clock gating on big data buses. And big data buses, we tend to have a control signal to say that this data bus is valid or not. And so we'll use that control signal as a clock gating to say, when this bus is not valid, stop the clock because we don't need it to be toggling unnecessarily.
Okay, thank you.
Next.
Scott Johnson, Spacely Packets. I was wondering what your opinions are on the areas where we can further improve the power efficiency performance of ASICs and network hardware in general.
I think there are many different techniques out there. I think one of our director of engineering, Sharda, has written a lot about that, and I would agree with a lot of the techniques that she's proposing or that we are already implementing. Things like decreasing the movement of packets through the chip, for example. That's where the advantage of the VOQ architecture is, that you're not unnecessarily moving that packet if it's going to get dropped. You drop the packet on ingress. And there are techniques to eliminate the need to go to HBM or external memory. Because anytime you go external memory, you have to expend more power to actually access that memory and actually pass packets through that interface. So we have new techniques to keep the control, keep the logic, which is say, as much as possible, prevent access to the external memory. And things like caching is one of we cache internal to the chip so that more often accessed data does not require going to that HBM memory. So we stay on chip. We have we have this architecture where, like I said, it's more pipeline replicated architecture. So in certain cases when maybe you don't have that many ports active on your chip, you can actually shut down big portion of your ASIC because we've divided our ASIC into parts, into pipelines, which for certain data from certain ports don't even access the other part of the ASIC, so we can just shut it down. So we continue to look for ways to save power.
Thank you.
We have a question online from Matt Pitak, unaffiliated. Great talk, Nancy. Early in the presentation, when talking about SIR-DES, you said that the serial interface runs faster than parallel interfaces. Network data is inherently serial when it arrives at the NIC. If serial processing is faster than parallel processing, wouldn't it be faster to omit the SIR-DES and keep the data stream in serial form all the way through the processing pipeline?
Okay, so the serial interface, the SerDes, the latest SerDes technology runs at 200 gigabits per second. So that's equivalent to running a clock at 200 gigahertz. And that's just way higher than any kind of ASIC process can handle. So we really need to divide that serial interface, translate that into parallel so that we can actually run the internal of the clock at a slower rate. So if you were to take the serial bus and make it parallel to 100 times. So a 200 gigahertz clock would then be a 2 gigahertz clock, and that is much more reasonable if we can handle it within the ASIC. So there's just no way we can process data that fast, and so that's why we need to translate into parallel.
Hi there, Andrew Gray, AWS, although I'm asking this for myself. So in talking about the SerDes in the past, there's been concerns about signal path length and things along those lines prohibiting the SerDes from going any faster. So where are we going to go from here after 112 or 200 gig SerDes?
Yeah, it's a 200 gig. I don't think I have the information to answer that question. I've heard that we can go faster, but I don't have the answer for that.
Gotcha.
Any last questions? All right, thank you very much.
Okay, thank you.